theorem, as Javier was saying yesterday. So today I'm going to discuss the putative existence of non-invertible symmetries in higher than 2 space-time dimensions. So this is a somewhat controversial topic, since everybody basically believes that this is the case, and actually our new common and global colleague, the artificial intelligence, particular Gemini, believes they exist as well. Yesterday we were discussing a bit. This talk the main objective of this talk is to describe some phases of symmetry that that are not so standard, and that will help, I hope, to clarify the overall picture. So this talk is somewhat independent from any particular reference, but the results that I will describe are contained in these 3 references here. So the first is titled Generalized Symmetries and Noether's Theorem in Quantum Field Theory, with Valentin and Horacio, who are both in the audience. The second is, for the purpose of this talk, this reference describes subtle obstructions to the validity of Noether's theorem in quantum field theory, that I will describe in due time. The second reference, ABA anomaly as a U1 symmetry and Noether's theorem, discusses the specific case of theories with the ABA anomaly, and how this can be understood as a standard, almost a standard internal U1 symmetry, and how this is not how this plays with Noether's theorem in quantum field theory. This article was again written with Valentin and Horacio. And then the last article, which I will discuss at the end, is called a generalization of DHR, that I will describe in a moment, to higher form symmetries. This is an article with Horacio, and I hope it will appear somewhere in 2025, or else some of us will commit suicide. So hopefully it will appear. Okay, so let me start with the motivations for this work, and they are very simple. So on one hand, we have the relatively recent claims in these two articles of the existence of non-invertible symmetries in higher than 2 space-time dimensions. These articles have attracted a lot of attention in the string theory and the condensed matter community, and the reason is very simple. Is because, although this type of more general symmetries were known since long time ago, in the 80s basically, in 2 space-time dimensions, they were not known in higher dimensions, and this explains the burst in activity. This is, I want to say that the claims are non-trivial, in particular, if true, for example, as they claim, they would explain, they would be the ultimate reason of pion decay, for example. On the other hand, we have the famous, at least in some part of the community, Doplitzer-Hack-Roberts reconstruction theorem. This is the culmination of 2 decades of work in the 70s and the 90s. And although this theorem is quite sophisticated, for the purpose of this talk, has a very simple corollary, which is that zero-form symmetries are groups in dimension greater than 2. Okay, so we clearly have attention. We clearly have a problem that the community, most of the community, has no pay attention because, probably they don't know about this body of work. But we think it's quite interesting. And finally, maybe similarly unrelated topic is Noether's theorem in quantum field theory. So maybe again not so known. This is not proven in quantum field theory, and it's not proven for very good reasons, basically because we have counterexamples. And some counterexamples are the graviton field, which is relativistic but has no stress tensor. The Maxwell field in 5 dimensions, which is a scale invariant but has no scale current. Electromagnetic duality, which is for the Maxwell field, and other examples. Now, maybe in the literature, these counterexamples have not been treated as they should because they are all free, okay? But today's talk, this will be important to understand the whole picture because actually we will see that a potential candidate, and at the end, a real candidate of a counterexample for an interacting theory are theories with ABJ-like anomalies. Okay, so are there questions about the motivations? Yes. So there is yeah. I would say so. There are two. We could say there are two statements of the theorem. One could be called the weak, and one could be called the strong. In few words, the weak is proven, the strong has counterexamples. What is the weak and what is the strong? The strong is the one that we are used to, which is the fact that if we have a symmetry in quantum field theory, for a continuous symmetry, there is a local Noether current as an operator in the theory. Okay, this would be the strong. This is not proven because, well, there are counterexamples. Okay, and the weak would be the fact that there are local twists. Okay, so for example, if I have a Noether current, I can integrate the current only over a compact region. Therefore, I have a local twist. So the strong implies the weak, but I could have the local twist, but not have the Noether current. Okay, and so this is proven in the using algebraic techniques, and this is not. And in the basically in this article, we understood why this is the case, and this was partly described by Horacio in his lectures. We can discuss later. Yes. Yeah, Maxwell indeed. Scale invariant. This is maybe you recall this is also related to another set of problems, which is whether conformal invariance implies scale invariance. Okay, sorry, the opposite around. Whether scale invariance implies conformal invariance, and this typically is called as a counterexample to that. So it's a theory that is scale invariant, but it's not conformal invariant. Particular has not a conformal stress tensor. Okay, and the reason is that the reason, as we understand, is that this theory, because of the theorem, I will explain a little bit later what is the theorem, but because of the theorem we prove here, this theory cannot have a scale current. So it cannot have also a conformal stress tensor because that could provide the scale current. Okay. This is a scale invariant, but not conformal invariant. I will explain the reason at the end of the talk. Yeah. No, this is the first. This is the first. Well, this is not the content of the talk, but the statement of Noether's theorem is that in quantum field theory, so the usual one is that if we have a continuous symmetry, okay, in the theory, that implies the existence of a local Noether current that generates that symmetry. No. But this is for the global symmetries of this model. These symmetries have the Maxwell is relativistic. I mean, it's we can discuss later. Okay. Yeah. Maybe we can discuss that because it's not the topic of the talk. Maybe we can discuss that later. But let me just say that there are examples in which we have internal symmetries, zero-form symmetries, completely well-defined in the gauge invariant sector of the theory, and they have no Noether current. And now we understand why, and that's it. But what I was just, I mean, the objective of putting this motivation here is that at the time, only 3 examples were known. Okay, only 3 examples. Okay, so the plan of the talk is quite simple. First, I'm going to describe 3 phases of symmetry. So 3 approaches to symmetry in quantum field theory. Then I will describe some ab initio concerns with non-invertible symmetries that are not directly related with the DHR theorem, and that for us were important to guide our research. Then I will discuss the case, explicitly the case of the ABJ anomaly. And then I will, if time allows, I will discuss the generalization. Well, in the case of the ABJ now, so this is basically the core of the results of the works. Here we will recover this anomaly as a standard internal symmetry with some peculiarities, but as a standard internal U1 symmetry. Well, we will see why it is a counterexample in this very same way to Noether's theorem. This suggests that there might be, so this is of course consistent with the DHR theorem, not with this research, and then suggests that maybe there is a generalization of the DHR theorem to higher form symmetries. Okay, and I will discuss this generalization. Okay, so I start. With three phases of symmetry. The first is the, we can call it, we could call it the standard one. It was described in the seminal article by Gallotto et al. And it is the approach that was nicely described by John McGreevy in John McGreevy's lectures last week. So this approach focused on the category of let me call for the moment topological maps. So let me call it like this. Defining these maps are defined over codimension P hypersurface in space-time, and the defining property of these maps is that they can be freely moved. Okay, well, this is the statement of topological, but well, they can be freely moved over space-time with at no cost. Okay. The case of zero-form symmetries, which is the standard case of zero-form symmetries, corresponds to codimension with 2p equal to 1, codimension 1. And in this case, these topological maps link with local operators. Okay, and because they are topological, we can shrink. No, we can put the operator here. Well, let me. Sorry. And this will define, so it was the original operator, and this define another local operator. So the symmetry acts locally. So this is the action of the topological map. Okay. Well, these topological maps might have labels here denoted by A, and to differentiate one or the other, and they can fuse. Okay, they can fuse in the usual way, and the fusion can be reduced. Sorry, this is N. Okay, and so they form what is known as a fusion category. It's a mathematical structure that I won't describe today, but it was you can see Paul's lectures last week about that. So they defined what people call a fusion category of topological maps. Okay. Now, from this point of view, there is a simple definition of what is invertible versus what is non-invertible. So here, invertible, we would say that so an invertible symmetry is a symmetry such that for every A, there exists some A minus 1, such that MA times MA minus 1 is M of the identity. Okay. And non-invertible would mean that even if for all A, well, even if for all A there is a conjugate, this is not an inverse. So in particular, MA bar is equal to M of the identity, but you also have some other things. Okay. Let me clarify that this definition of what is invertible and what is non-invertible is a little bit deceptive for a reason that I will come back in a little while, and it will be clear why. But for the moment, let's take the standard definition. So let me say that these maps in quantum field theory, these maps can be generated by operators in the theory, equivalent just by simple commutation. So so there are operators. Let me call them T hat to denote that they are real operators in the theory. By the way, here I'm not going to think that the system is in the Euclidean formulation or a statistical, or I'm not going to assume like equivalence with defects. I'm really in the quantum theory. I want to talk just about operators and maps over operators. Okay. So these topological maps are maps over operators, and and they can be created with actual operators of the theory via commutation. So for example, if I have a region, have the algebra in the region, then there are operators T hat effective, so such that by commutation they generate the map. What this means, you can see these operators, this T hat, as intertwiners in the category of topological maps, intertwining the identity representation with whatever representation you are interested in. For example, in the talk by Germán, he considered the operator D, and then, moving it to the right-hand side, he gets the transformation. Okay. Now this, so in the standard, so an example also, just to put, I mean, maybe this is not usually explained, but in a very simple example is take an invertible symmetry with a symmetry group. Then this operator, this T hat, is just the global symmetry operator. These topological maps are just so acting over some operator. It is just the usual conjugation. Okay. The usual conjugation, and you see, of course, that trivially this intertwining relation is satisfied. Okay. Now the point is that in general, in the standard, well, the way people in the standard formulation describe this approach, the T operators and the topological maps are kind of thought to be one and the same, and this is, of course, sometimes possible and useful, but it's important to see the difference. And the difference basically is that these topological maps are, as we said, topological. So there is one map for any region of space-time, and such maps are consistent with each other when acting on the operators. And but these are actual operators of the theory. They don't need to be topological. Okay. They could be topological, but they don't need to be, and there are examples where they are not. And still they satisfy the commutation relation. An example, for example, is just a twist that now, instead of being the global twist, I just consider a local twist over a compact region. This is not topological in the usual sense. It's an actual operator of the theory. Still, via this commutation relation, it affects, I mean, it creates the topological map. Okay, the second approach is the algebraic theory of superselection sectors. This or DHR, okay, WHR and Roberts. This was developed in two articles in 1971 and 1973, and it basically it basically put the focus, instead of in the category of topological maps, in the operators of the theory, it put the focus on the category of certain maps, rho, acting on the observables of the theory, where the observables of the theory are the the subalgebra of all the operators that is invariant under the symmetry. Okay, so let me repeat it. So instead of topological maps acting over all operators, they focus on certain maps that I will define in a moment, certain maps over a subalgebra, which is the algebra that is invariant under the symmetry. Now, the defining properties of these maps are not that they are topological. The defining properties of these maps are that they are localizable and transportable. What does it mean? This means that a part of this label, which we will have also a label like here, a part of that label, they also carry a localization region, okay, R. And then so on the algebra of operators that is outside, it acts trivially, okay? So it only acts non-trivially. It only acts non-trivially on the operators in region R, okay? This is the notion of localization. The notion of transportable is just to say that there are intertwiners, there are operators, there are observables in the theory that transport to another region, okay? And these I are invariant under the symmetry, so they belong to the operators that are invariant under the symmetry, okay? So so this is non-standard. This is not so widely known. This is what these people define. What is interesting is that the first most important thing that these colleagues prove is that this type of maps also form a category. Okay. So we have rho A, rho B equal to sum and ABC, rho C. Okay. So this n is of course not the same as this n. They are all, let me call it n tilde. It's another fusion category, okay? But they form a fusion category. And actually what they were able to prove is that in relativistic quantum field theory, this category, it's necessarily braided. So this is the main part of the DHR theorem, is necessarily braided into D, but is symmetric in the greater than 2. Okay, what does it mean that is symmetric? Is that, there is a permutation symmetry, so therefore basically the braiding can only have eigenvalues -1 or +1, so there are no Anyon statistics in the greater than 2. Correct. I'm not going to go over that derivation, but let me just say very quickly. So basically, as I said, these are associated to some localization region. Okay, so this is rho R, for example, A, and here I have some rho R prime with the same label, for example. And the point is that the important point is that there are transporters, okay, that belong to the algebra of neutral operators, and with those transporters, I can move things around. Okay, and I can define, through those transporters, I can define an statistics operator. And then I can derive that statistic operator can only have ±1 eigenvalue, cannot have some phase, okay? So, okay. No, it doesn't matter. It doesn't. I mean, okay, yeah, good question. So the one row is associated to one region, but of course, because of the transportability, what you really need, I mean, the fusion is really over the classes that defines the transported region. Okay. Are well defined and fixed and constant. Yeah, are well defined, fixed and constant. Yeah. Okay. So now, if in the standard case, the intertwiners generating the topological maps are basically the symmetry generators, in the DHR approach, the intertwiners generating these DHR maps are the chars. Okay, so psi r times the algebra in some region is rho r a on that algebra times psi of r. Okay, so so there is a very precise and deep or insightful, you want whatever you want to call him, way in which the standard case, the standard approach is and the DHR approach are dual to each other. One is focusing on the category of the symmetry generators, and one is focusing on the category of the charges. Okay. Okay, and finally, we have, yeah? What? Well, yeah, the theorem, so it goes in various steps. So first that, yeah, the theorem, it says, first I define these maps, then thanks to transportability, to this property, I can prove that they form a category. And then because also of this transportable, I mean, this thing that I explained, I prove that it is or braided into D or symmetric in D greater than 2. Symmetric means that there is a permutation symmetry, that the statistics needs to be plus or minus 1. So there are fermions or bosons. This is a proof of the spin statistic theorem. No, of course not. No, group, no, sorry. This is, okay, good question, sorry. No, of course, for a moment, this is, so just this is the only thing that has been proven, okay? Now, the point is that you can prove from this that the dimensions of the quantum dimensions of this category are all integers, okay? So in this case, dA belong to n plus is rep G. Is typically and then the point is that the only possibility for all the dimensions to be positive integers is to be rep G, and then of course this is the fusion of representations, the superselection sectors, and you can reconstruct the group. It comes later. Okay. Okay. So and then we have yeah, we can say Bariloche, as Horacio called the other day. Bariloche is or hat duality violation approach. Okay, this was described in Horacio's lectures, and it has been developed by some of us there, including Valentin, Horacio, Marina, Diego, and more people. The original question of this was actually, so the original motivation maybe to understand it was, can we unify both approaches? Okay, so and to answer this question, well, first, this in principle was only for zero form symmetry, so there was already a problem for generalizing to higher form symmetries. Okay, there was that problem, and also at the time we didn't have clear all this mathematical structure. So for us at the time, it was kind of simpler and more physical to leave the idea of maps. So to leave the idea of this kind of abstract map, or this kind of, well, people don't see it as abstract if it's topological, but still, yeah, to leave that kind of idea behind and to focus on the, so the focus in this approach is on the combined algebra of the intertwiners, so of the charges and the twist. Okay. Notice that this is, so two comments. So sorry, I define it there like this. So this t hat. Okay. There are two comments I want to do. So first is notice that this doesn't form a category. So these are operators in the theory, and what they form is an algebra. Okay. Sometimes we could extract a category from it, but properly it is an algebra. Okay. It is just the algebra of intertwiners of the maps. Okay. Also, another remark is that in this case, what is symmetry and what is charge operators is kind of blurred in the description, and the description becomes more symmetric. Okay. This actually parallels the scenario with order and disorder parameters, no? In which what is order, what is disorder is a little bit of convention, no? And here actually, well, this you could call the order parameters, and you could call the disorder parameters. So basically, it really goes to the physical part of the story, which is the physics of order and disorder. Okay. What? Fusion category. Not what? No, fusion category, yeah. But I just mean to differentiate between algebra, between some OPE. There is a kind of, sometimes people also equate having an OPE with having a fusion category. Having a fusion category is something very clean, no, that was explained by Paul, and having an OPE is another thing. Maybe from an OPE one can extract a fusion, but it's two different things. Okay. So, well, basically the approach is that, so the focus is on this one, on this algebra, and the fundamental observation is that order parameters, well, order or disorder parameters, such as these ones, violate Hug duality, which is a property that I'm not going to describe because we are not going to use, but maybe you can check Horacio's lectures in certain region, okay, in certain region of space-time. Okay. This gives an intrinsic definition of what is an order parameter that doesn't require a Lagrangian, doesn't require, so it's quite powerful, and well, basically the past 5 years we have been extracting consequence of this observation. So the main consequence, for example, is that well, order cannot exist without disorder, no? Which is something that we all know, but here you can prove it. So here you can see it transparently that whenever you have an order parameter, you have a disorder parameter, and they are constrained. Their statistics are constrained by certain relations. Okay, so I just wanted to explain a little bit the 3 different approaches, because sometimes, well, the results that we have described sometimes are argue that, well, it's because of certain assumptions. So I just want to say that the physics that I'm going to describe, whether the non-invertible symmetries exist or not, of course, it doesn't depend on whatever definition you take. The physics happens in all approaches. Okay, are there questions about some of these? Are there more questions? Yeah. Not exactly. Not exactly. Very good question. No, not exactly. I can explain later. So it could have more operators. The commutant. So yeah. So that's a very good point. So okay. So A of R commutant might not be equal to A of R prime. Okay. The only thing we need for the theory to be well defined is that A of R prime is contained on A of R commutant, okay? But this algebra could contain more operators. We call them Hug duality violating operators, and exactly the intertwiners are always those kind of operators, okay? You can see maybe Horacio's lectures. I'm not going to go over this thing. Okay, so let me see some ab initio concerns with non-invertible symmetries in D greater than 2. Okay, the first is more a remark. So remark. Is a remark. It's just that the existence of a non-invertible topological map. So the existence of MA with no inverse doesn't imply that symmetry is non-invertible. So this is related to the remark that I was saying here. So first I define it exactly that way, no? And now I'm saying that this is not exactly the case. And the reason is basically that imagine we have an invertible symmetry, so we have invertible topological maps. So with the usual fusion rule. Then we can always add 2 of those or many of those, and by doing that we get further topological maps over the algebra, and these are non-invertible. Okay, so a particular example of this, is just by defining this conditional expectation, which is, for example, for a finite group, it just this definition, okay? So I just add all the operations in the group. This conditional expectation is well defined over all the algebra, so it's topological, and it's a projector. It's a projector onto the invariant algebra, so it's as non-invertible as it can be. And still, we don't want to say that, okay, that because I can do this, I have a non-invertible symmetry, no? So we want to eliminate these cases from the definition, no? And the correct statement is that we have a non-invertible symmetry when I cannot find a definition of the theory in which the non-invertibility just come by, I don't know, operations of some sort on the invertible topological maps, okay? This is the correct statement. So in practice, what it means is that, okay, you have a theory and you found a non-invertible symmetry topological map, then, well, you should make some effort to prove that it doesn't come from an invertible one, okay? Now, the second is really a concern. So, and it deals with the statistics of phi, of the charges, and also their levels, okay? Their levels here. So in general, so we have defined what is non-invertible and invertible in this standard law, okay? But we could also define it here, no? So we have, for example, an invertible symmetry group, so an invertible symmetry. Then we know that the charges, so in particular this fusion of the HR sector, is the fusion of is the category of representations, is the category of the superselection sector. So basically, we can define invertibility for having the group theory like fusion for the topological maps, or the category of representations for the charges, okay? Also, the same for similar for statistics. For example, by the way, yeah, in 2 dimensions, for example, we know examples that in which the category is not that of a group. For example, it's a quantum group, and then we see that we can also see that non-invertibility by looking at the category of superselection sectors, which is the representation of a quantum group. So there is no way we have there is no example in 2 dimensions in which you have a non-invertible symmetry and in the topological maps, and the category of representations of the charges is the category of representations of a group. That doesn't make sense, okay? The same with the statistics. So the statistics of the charges that, for example, in 2 dimensions are anionic, no? And that corresponds to more general symmetry structures, while when we have groups, we have fermions or bosons, no? Well, the problem, so this is completely standard, and the problem is that the examples that have been found, so in particular the examples in those papers, the charge operators are just the top loops, for example, top loops. And these are labeled by representations. So I mean, this runs through the integers, okay? So it is kind of strange that we have charges that runs through the integers and the symmetry is non-invertible. So it seems something is missing. And the same with the statistics. In higher dimensions, there have not been found examples in which we have non-trivial statistics. Okay, so that's also strange. It's just some concern. Okay, some concern with that result. The third concern is about transportability. Transportability of topological maps of this MA. So, for example, for the ABA-like models, as I will describe in a moment, for the ABA-like models, we always can find. So we will see that it exists the, let's say, the global symmetry intertwiner. So this UG. Okay, which is gauge invariant and which is topological. Okay, in the sense of, well, that I will define in a moment. Now, the problem that people have pointed is that well, when I try to define the topological map for compact regions, then I find problems with gauge invariant. Okay, because of the, well, I will review it in a moment. But this is kind of strange because if this guy is topological, I mean, if this guy is the global generator of the topological maps, then for any region, it will do the map, okay? Of course, Probably expressing that in terms of the field of the fields of the theory for an interacting theory probably is difficult. I don't know, but this commutation relation, if you have this operator, if you prove that you have this operator, this commutation relation uniquely fixes this map. Okay, so it's like the parent of all topological maps, if you want. So it's a strange. I mean, the claim that such maps do not exist it is at odds with the fact that these operators exist, which everybody agrees, as I will comment in a moment. And more important, and this, by the way, this point that I'm going to mention now is, well, we asked artificial intelligence what, well, we asked first about non-invertible symmetries. Well, it told us, whatever is the gender, that the non-invertible symmetries exist. Then we told him, like, well, but we have the DHR theorem. What happens? He told us, well, this is very insightful question, but there is no problem. And there is no problem because of the thing that I'm going to mention, okay? So, I mean, which is wrong, I mean, which is I'm going to argue that is wrong, but this is the argument that the artificial intelligence gave. So, so zero-form symmetries, okay, act on local operators, okay? That's a true statement, as we mentioned here. So it acts on local operators just by contraction, no? Because the symmetry is topological. For example, this is the case. This is the case for so this is actually non-trivial. Non-trivial in d equal to 2 with the Berlin lines. Okay, we have seen examples last week, and this is of course very, very well known. For so in the cases that have been found in greater dimensions, okay, for d equal to 2, as already those articles acknowledge that the symmetry that they find, so this topological map they find, when it acts on local operators, it acts as an invertible symmetry, okay? Actually as a U1 symmetry, okay, for reasons that I'm going to describe in a moment. But the non-invertibility, the claim is that the non-invertibility only happens when we let this MA acting on a non-local operator, like a top loop with certain charge. Let me call it G tilde, okay? Well, this is the claim. This is what everybody says, and this is what the artificial intelligence now says as well, that the non-invertibility is due to the action of the fact that we have more freedom in the action. Now we can let act the topological maps on non-local operators as well. Okay, but this is a problem. This is not possible. Okay, and for us it was really like a guiding principle. So this is not possible. And the reason is that, it's very simple, is that non-local operators, so non-local operators, such for example as the top loop, can be written always in terms of local ones. Okay, so let me put some examples. So for example, if we have the top loop in Maxwell field, this is equal to the top loop with charge G, this is equal to e to the G, integral of the electric flux, so times the electric flux over certain, let's say, certain surface. Okay, so the top loop defined in a certain line, in a certain closed loop. Well, is the exponential of the electric flux over any surface bounded by that loop. The same with the Wilson loop. Okay, now I just change. For the magnetic field. Now you could say, well, but this is just for the free Maxwell field. What about other theories? Well, for the case of non-abelian gauge theories, when we have Wilson loop in representation R, this was explained in Horacio's lecture. We derived it in one of, old paper. So I refer to Horacio's lectures here, but it can be written in terms of local ones. It is more complicated, of course. And today, now I'm going to talk about which is the key case here of importance. I'm going to talk about the top loop in ABJ-like theories. Okay, how to write it in terms of local fields. But if any of these operators I can write it in terms of local fields, it is an inconsistent statement to say that the symmetry acts non-invertible because how I write the operator, I mean, it's completely unphysical. It's just an operator of the theory. Okay, so clearly, if I can write it in terms of local operators, and you tell me that on local operators is a U1, well, in the non-local is going to be a U1 as well, and this is going to be. Well, this is going to be transparent. Are there questions until here? Yeah. Okay. Yeah, 10 minutos. 10 minutes. Yeah. Okay. So, okay. So now I'm going to discuss the case of the ABA anomaly quite fast because too much time. Okay, so so I'm going to discuss the particular example of action electrodynamics. Well, yeah, let me see. Yeah, action. Let me put it. The Lagrangian of this theory is basically, let me be a little bit, is basically the free pion. Plus the free Maxwell field, plus this almost topological interaction. Okay. And well, the nice thing of this is that the equations of motions, which can be derived directly, actually expresses the anomaly. So if one of the equations of motion, I can just write it as d mu, j mu, equal to 1 over 4 mu. F tilde F, okay? And this, sorry, where J mu is just mu d mu pi, okay? So I can even go a little bit further, as Adler did, no? And write this as write this equation as the conservation of a modified current, okay? So where the modified current is just, well, it's just the original one. Minus some f times a, okay? Some f tilde times a, okay? Now this current, of course, this tilde current is not gauge invariant, so it is not an operator on the theory. But I can generate a charge which is gauge invariant. Let me call it q tilde by integrating j tilde 0 over the full space-time, okay? As I said, this is over the full space-time, so this is gauge invariant, but this generates this global intertwiner that I was mentioning here, that is, well, is the global intertwiner of topological maps, and is gauge invariant. Now the question, of course, is whether, so exponentiating the charge, and defining UG equal to e to the I alpha q tilde, this in principle is a potential candidate for a U1 symmetry of the theory. Of course, further conditions must apply, and the conditions basically are what I mentioned here in the standard law. No? So the conditions are that the action of on local operators is local, okay? So and is consistent over all the full space-time. So therefore is topological, and for that we just need to check two things. We need to check that when I study the commutation relation between the modified charge and the fields of the theory, namely pi 0, E, B, and well, I have to study all the commutators with the local fields of the theory, and I can do that using canonical quantization. These computations are non-trivial because of this interaction, but everything conspired so that all local operators are invariant except for the pion field, okay, which is basically gets moved by mu. Okay, I can also compute the commutation relation of this q tilde with the canonical stress tensor. and it also gives me 0. So this, well, for us, this is clearly a proof that this is an internal symmetry. We have a topological maps via commutation relation in any region, and the symmetry is conserved. So what is strange about this symmetry? No, why it has, well, created so much attention and so much confusion? And the reason is that there is, well, your concern could be, well, okay, you have proved me exactly this, no? You have proved me how it acts on local operators, but, well, the claims were about the action on non-local operators, so what is happening on that, no? But in principle, if what I said is true, the action on the top loop should be completely determined by this action, okay, here. And this can be proven. And the way to show it is to understand the one-form symmetries of this theory here. And the one-form symmetries of this theory here can be understood just by, well, sorry, I forgot one equation of motion. So we have this equation of motion, and we have also the conservation of the dual field strength. And now I can write these equations. I can write it in a different way. I can say that they are the conservations of two form fields. So this. Okay. And where I define, well, this is defined in the usual way, is the dual of the field strength, but this G mu nu is defined as F mu nu. So it would be the usual F mu nu, but it has now been dressed by the pion field. Okay. So these equations are, of course, the equations of the Maxwell field. So this is very good, because now I know what are the one-form symmetries. It's just, the non-local operators are just these operators here, are just these operators, the top loops and the Wilson loops, integrations of the electric flux and the magnetic flux. The only thing is that, crucially, the electric flux now is not just the electric flux, it's the electric flux plus some contribution, some dress contribution from the pion field. Okay, this is important for the operator to be topological. If not, if it's just the electric field, it's not topological. Okay, it is this contribution that makes it topological. And so the non-local operators are basically, the more general non-local operators are dions, okay, with some charge Q and some magnetic charge G associated to these two form fields. And what is interesting here is that from these commutation relations, which are completely local, and this observation, the fact that the pion enters in the definition of this modified electric field, one can derive this equation here. So this U tilde, so this UG, let me call it U tilde G. So this UG minus 1. Okay, this is equal to, let me write it right. Sorry, let me put here lambda. So some chiral rotation, okay, some chiral rotation to the minus 1. And this is equal to d q plus lambda g. Okay, and maybe for the people on the audience that are experts on this thing, well, they will recognize this equation. This is just the Witten effect. Okay. It's just the Witten effect. So it's the effect that when we have some magnetic charge, that magnetic charge under a chiral rotation gets mixed with an electric charge proportional to the chiral rotation and the original magnetic charge. Okay. But the interesting thing is that we have derived the Witten effect just by local commutation relations. I mean, so whatever is the physics of this, it's not. I mean, it cannot be. So it has to be a U1. I mean, there's no in every correlation function that I insert these guys. I can go back to my expression in terms of these fluxes, and it will be invariant under a U1 symmetry. Okay. And in fact, well, with this I finish because I'm running out of time. So I will not have time to go through the last part, but let me say that now we have, so what are the symmetries of this system? So in principle, we have this U1 modified, so this a U1 chiral symmetry generated by this modified U tilde G, and then in this theory, when I ultraviolet complete it, it will always come from a theory that has electric charges. So this will break part of this of this one-form symmetry, the actual symmetry of the one-form. So this is the zero-form part. The one-form part is actually U1 times C, okay? And then we have an E generated by these fluxes, okay? By the G and F fluxes. And then we see that we have two U1s, okay? But not only we have two U1s, they interact one with the other through the Witten effect. But then if I make a U1 chiral rotation, no, here in la lambda, when I make the 2 pi rotation, I have to come back to the same place. Okay, I have to go to the identity. So let's say when lambda goes to lambda 0, so if the radius on compactification is let's say 0, is lambda goes from 0 to lambda 0, then when dq q plus sorry it was this was something like this. Well, doesn't matter, some details. But when I go to lambda 0, okay, here, then this has to go to this has to be equivalent to Q again as a non-local operator, because I didn't do anything. I did a 2 pi chiral rotation, and so sorry I didn't have time to explain this, but this at the end of the day in this theory. Sorry, so also, let me write it now in a proper manner. So this has a coupling. In principle, I let it completely free. And but this let's say compatibility condition between the U1 zero-form symmetry and the U1 one-form symmetry tells me that at the end of the day, that this mu, this 1/8 mu, has to be quantized in terms of the minimum electric charge of my theory. Okay, here this is f of pi is the decay constant, and so this is anomaly quantization, yeah. So and we see here that anomaly quantization just follows by this compatibility condition, and give us a physical interpretation of the anomaly quantization condition. Anomaly quantization coefficient. This n here is just telling us how much faster is moving the chiral rotation on the pion field here than on the non-local operators. Okay. Well, how much I have done? Yeah, it's on. Okay. Well, so yeah, I won't have time to explain this generalization. So please ask me later, and thank you very much. Oh, I will. Yes. It's actually very simple. Yeah. Let me just erase something fast. So let me just erase. No, yeah. So the 32nd part is just the observation. Well, so basically this suggests that probably non-invertible symmetries doesn't exist at all in higher than 2 space-time dimension. These people prove it for zero-form symmetry. The question is what happens for higher-form symmetries. Okay, and then, well, the main observation of the work that we are doing with Horacio is just that, the charges, so the analog of these endomorphins, no, that here you remember that we had for the zero form, we have this localization region, which is a ball, no, and we have 2 balls, and we can exchange it, and we can prove that the statistics are trivial, are bosonic or fermionic. So now the charges for one-form symmetry are loops, okay? So I can define the same thing, and let me draw it like this. And there is an effective, if you want, dimensional reduction. So the main observation is that there is effective dimensional reduction, and on algebraic grounds. And then from this point of view, I can do the same with the loops. So I can move them I have a space to, the main point of these theorems is that when I have more space-time dimensions than 2, I can move the things and nobody stop me. No? And because of causality, that forces the statistics to be trivial. And the fact that that forces the statistics to be trivial forces the dimensions to be integers, and the fact that the dimensions are integers forces that for the dual category, forces the dual category to be a group. Now, of course, the devil here hides in the details, and actually there are many differences. So this is a very simple idea, it's just, well, but the problem is that, well, from a precise way, higher form symmetries are always spontaneously broken. They are, I mean, the non-local operators, no, the Wilson loops and Toff loops always have some expectation value. It's not like a psi in a theory with a zero form symmetry, whose expectation value is just directly 0, okay, in the symmetry. No, and this, well, this actually, so we need to generalize this proof to spontaneous symmetry breaking. We need to actually consider other type of topologies that you were. So there are many details, but the main idea is this one. And notice that one last thing is that this dimensional reduction, I can do it for the, let's say, for the size. Let's say that the size are the Wilson loops, but I can do it for the dual ones, which are the Toff loops. I can do it for both of them, and then I get the result that both the charges and the groups, so both the charges and the order and disorder are representations of groups. So it can only be abelian group. So it's a stronger theorem. So basically, higher form symmetry can only be abelian groups. Okay, and this explains also what is seen, because they are all abelian. Okay. In D greater than 2, yeah. Sorry, can you repeat? Yes, yes. Well, but that is okay. That is just like so there are different things. I mean, of course, if I have a Wilson loop and I have a Toff loop, okay, these guys have non-trivial commutation, okay. Okay, and this is basically the braiding that you are pointing at. It's just the braiding of the one form. I mean, it's just understanding the commutation relation of the Wilson and Toft as a braiding, which you can do. What? That relation between order and disorder, and that is not what is playing the key point when deriving the fact that these are abelian groups. No, in different. Sorry, yeah, in two space-time dimensions. So yeah, very good question. So in two space, so here is this is 2 plus 1 or 3 plus 1 or whatever. In 2 plus 1, so in 1 plus 1, I have some line. No, this is my space. No, and then I have time. And then my region is, if I have 2 regions, for example, well, they live in a line, okay? And it's not the same, so I cannot, I mean, when I move this thing around, I have to cross the localization of the other. You see? So if I want to move to define a statistics, I have to cross the other, so they have to interact. I cannot do it without interaction, and that's basically the braiding is basically the interaction, the price to pay in 1 plus 1, because I cannot do it freely. I mean, I can explain later more the detail, but it's basically that. I mean, it's just, yeah.